Very good afternoon, students. So now in this session, we are going to discuss about uh, three topics like called closure, and then we will talk about what is the shuffling over here, and then we will talk about the and partitioning also. So we'll talk about partitioning in detail. So let's start with the closure. So what is the closure? So now just to understand the closure, first let's take an example. So I'm just writing one example called, let's say, counter is equal to 0. This is a variable, and I'm creating one RDD called sc.parallelize, and then I'm calling with the data. Let's say data contains some data. Then I'm defining one function. My function name is, let's say, increment, and it is taking a variable called x. And in this increment function, let's say I'm using two variables like a counter, global counter, and then I'm using a counter plus equals to x. I'm increasing with counter with the value x. Okay, this is quite simple example. Now let's say if I write the rdd dot for each, if I write this and if I call the increment function, okay. So now here I am printing the counter value. I'm just printing the counter value. Okay. So what happened with this code? I just want to make you understand. As you know that in a Spark, what the Spark do? So Spark actually break up your processing, or you can say break up processing of the RDDs operations. Okay, into task, and then uh, this this each is executed by the executor. So how the Spark actually behave in this way. Okay. Now for this example, if you are thinking that this counter variable we are increasing, so there are two things. This code has been written in the client side. So this is your client code. Okay. This is client or driver. This is your driver. And then when you execute this, that means now let's say your RDD is divided into this three part, and there are three executor running. This is executor 3, and this is executor 1, and let's say executor 2. Now this is executing on these three different areas. So now what happened, what the closure means now. Okay, so now the behavior of this code is actually, you can say this behavior is undefined. I'll just tell you why it is undefined, or you can say may not work as intended. Okay, so may not work as intended. Now very important thing, you should know that before executing, or you can say uh, prior to execution, what the Spark will do, Spark will compute the task closure, right? The task closure. So now we will understand the definition of the closure. First we'll understand the definition of the closure, then I'll come back to this example. Now the definition of closure says that the closure is a variable or it can be a method, okay, and which must be visible for the executor, this part. So how the variable will be visible, or function will be or method will be visible to the executor, so that they can just to perform its computation on the RDD. So here in this example we have a for each function. So here we will call this one, and it will, for each function will actually perform the operation on the RDD. So now this closure, I'm just talking about the closure. Actually what happened, this closure is serialized. So why serialized? Because it can travel on the wire or in the network. So it is serialized, and then it's sent to the each executor. So before executing the task, this process happens. Okay, now you can visualize in the way like there is a variable is there, and variable say that is sent to, you can say, executor within the closure. Okay, now what happens in our example, let's say we have a counter variable in our function called for each, or in a method called for each, which is, this counter variable is no longer the counter of your driver node. Try to understand this point. This is very important. So when I say this counter is in the driver, this counter is of the driver. This, before executing this task, this part, the closure will be created. Task closure will be created, and then this variable will be closure will serialized, and then it will travel to the executor. Now this counter is now different from this counter. Okay, now on the other side we can say that the counter which is available on the driver side is no longer visible to the executor. So that means now these two counters are different. Okay, and this executor see only the serialized counter which we have just sent before the execution of the task. So now the whole concept, just what I want to tell you is that now in this kind of scenario, in some of the function, the value of the counter will, value of the variable will be different, because value which is of the variable which is available in the driver side is different from the executor side, then in that scenario there will be undefined behavior. Okay, now if we check the local mode, let's say if I take a local mode, when I say local mode, I'm talking about the single machines. Okay, in local mode what happens, your function, your function, let's say your for each function will execute within the same JVM, okay, as the driver. So now in the single machine the driver will be having same JVM, that means object will be same, so driver will be there in itself, so that it will refer to your original counter. Now in this scenario there will be no impact on the counter because both are on the same JVM. But in the cluster mode, okay, in cluster mode there are different values of both counter. That means I'm talking about driver and executor I'm talking about. So now just to avoid these kind of situation, what we need to do, just for this we should use accumulator. Okay, and this accumulator is used for well defined behavior. Okay, now let's see the definition of the accumulator, and we were going to do this accumulator in detail in the coming session. Just to very high level idea about the accumulator, let's see the definition. With the accumulator, what happened, that safely you can updating variable. So this accumulator will help us in safely updating the variable when we have an executor is split up across the worker node in the cluster. Okay, then accumulator will take care of each and everything. Right now, how the accumulator will be used, we'll discuss later. Now, just to understand this problem and this closure concept, so let's take another variable, or you can say let's take another example also. Okay, so let's take another example. So let's say I have an RDD. Another example means another function which can also impact this thing. So let's say RDD for each, and we have a println. Okay, or we can use like RDD dot map and println. So if we use these kind of functions, then we have some kind of problem, because with for each there will be different executor, and if you are using in the cluster mode, then there will be problem. So let's say if we have a single machine, in single machine what will happen, it will generate the expected output, because the counter variable is in the same JVM, both the counter variable will refer to the single instance of the counter, then there will be no problem. But in the cluster mode, now in the cluster mode, the output to STD standard output, the output to the standard output is actually now what does it mean, that the standard output is actually outputting now to the writing the executor STD out. Now it is writing to the standard output of the executor. Okay, so your STD out on your driver side won't show these stuffs. So that means there is a difference when we write this println on executor. When I say println is using the STD out, that is standard output, and it is now writing to the executor's standard output, not to the driver output. So that is why there will be a different behavior, unpredictable behavior. Now just to avoid this, what we need to do to avoid this, let's say just to print all elements, what we need to do, we have to use collect, and collect is actually an action whose data comes to the driver side. So we can use rdd dot collect dot, let's say for each, and then I can write println. So now it will show you the output into that. But this collect can run out of memory. Why? Because when we have a large RDD, that means it is directly coming to the driver part, then it is a problem. So to avoid this, we can use RDD dot take 100, and then we can call for each and then println. Okay, this is the how we can deal with this. And otherwise, like another option, good option is we can use the accumulator, and then we are going to discuss that. So now let's talk about the shuffle. So what happened in Spark, certain operations actually triggers an event, and which is called a shuffle. So you can say shuffle is a Spark mechanism for redistributing your data, so it is grouped differently across the partition, right? But this shuffle operation is actually involves your copying the data across executor. So what this shuffle do is, or you can say involve copying data across executor, or you can say machines. Okay, now what happens, let's say you have, just to take an analogy, let's say you have two boxes and you have kept some number into that, so that is your data. Now you want to arrange those data in some different order. So what you will do, you will take out all the data, and then you will keep it in a memory or a disk, and then after that you will redistribute it, or based on some aggregation function or something. Okay, so that means it will involve copying all the data from all the executor, all the boxes and all the machine. That makes this operation little complex and costly also, costly operation. So example for this kind of functions are like reduce by key. Okay, so now reduce by key, what this reduce by key do? Reduce by key generates a new RDD. It generates a new RDD where all values of single key combined in tuple. What does it mean? Let's say in different executor, let's say in 5 executor you have a 10 same key, the value of the key is 1 and it is presence is, let's say, 10 times. So now in one executor you have 1 comma some value a or 1 comma or some other value. So you have different presence of the key. So what it will do, group by key, it group based on the key, let's say 1. Okay, and then it will apply any of the aggregation function on the value of those data in different executor. It will apply the aggregation function on the value. So now that become a tuple. So when I say tuple, combining tuple, the tuple will be look like a, let's say k is a key, and then the result of executing against the reduce function against all values of that key. Okay, so this is the result operations we have. So this is some kind of aggregation function we can apply onto that. Now this value part is actually, you can say, the values must be co-located. Okay, why co-located? To compute the result, that is the value available on different machines. So it will co-locate all the data, and that means that is called a shuffling and that is called a copying. So it is something similar to the process of MapReduce. Now I can give the definition of the shuffle. If I say definition of shuffle, so what is the definition of shuffle? It says that it reads all partition to find all values for all keys. Here we discuss about only single key 1, but it will do the same thing for all the keys and bring together values across partition just to compute final result, and again for each key. So this is about the, you can say, definition of the shuffle. Now what are the different operations available, or what are the different operations which supports the shuffle? So we have repartition, we have collapse, we have group by key, reduce by key, and you can say join, and many other. If you remember in the last session I talked about this collapse is not used for shuffling, but it is avoiding the shuffling, because if I decrease the number of partition, let's say from 5 to 2, the data available on those 2 partition will not move. But in normal repartitioning, all the data will come and will shuffle and then copy it, and again it will give you the another kind of data in those partitions. So that means it's not a completely shuffle. So it is avoid up to some extent. Now very interesting thing about shuffling over here is like, what is the performance? So now the performance impact will make you more clear about what is the performing impact of shuffle. Okay, because we are copying the data, that means this is very expensive operation. Okay, so that means why this is expensive operation? Because it involves, what it involves? It involves disk IO. Right, so this involves disk IO. It involves disk IO. It involves, you can say, disk serialization also, and it involves network IO also. So these 3 things it involves, so that it become an expensive operation. Now when we say shuffling, it actually generates the map task, and this map task is not a map reduce task. The nomenclature is same. It generates map task and reduce task. That is why I told you that implementation of map reduce is something like that. Okay, we are not actually implementing the map reduce, but we are using the concept behind that. So what is map reduce will do, map task will do? Map task is used to organize the data, and reduce task is to aggregate. So while organizing, I need to take the data from different ways, and then we need to aggregate based on some logic. Either we are using sum or counting or whatever it is, right? So now with this behavior, the result is kept in memory until it fits, and once it's not fit, that means otherwise what will happen? It will spill, and it will spill to disk. Now spilling to the disk is actually creating an overhead, or you can say additional overhead of your disk IO as well as your and garbage collector. Okay, that is why this operation has a performance impact, right? I'll just show you the difference in the next session. What is the difference between the group by and reduce by key? This is very interesting, and then I'll show you one example use case also. Okay, so now let's talk about the partitioning. So let me recap the few things. When we talked about HDFS, let's say when I talk about the HDFS, in HDFS we use a block. Okay, and those blocks is actually a degree of parallelism at the storage level. Whereas when I talk about the map reduce, so in map reduce we have a input splits, and these input splits are the degree of parallelism at the processing or at processing level, and it is in the map reduce. And when I talk about the spark, we have partitions, and this is again a degree of parallelism at processing level in spark framework. Okay, now you can say that if we have more partitions, then we can have a processing maybe faster chances are there. The meaning of this is like when we have a large data, so this large data you can't store in single node, so that we need to, or we have to partition. Okay, now this behavior, this process of partitioning, the Spark actually do automatically. Spark automatically partition your RDD, and then after that it distribute partition across different node, right? So now if I give a definition of the partitioning, then I can say, or a definition of a partition, I can say this is a atomic chunk of data. That means this is a logical division, not physical, which is stored in or stored on node of cluster. You can say that this is a basic unit of parallelism. And you are aware of that, how we can do that. RDD is SC dot parallelize data and then the number of partitions. So this is the number of partition. So if we increase parallelism of the Spark processing, that means we are increasing the number of executor. Okay, and the number of executor, if I increase the number of executor, that means we are increasing the partitioning. So this is basic concept about the what is a partitioning. Right, now let's talk about the very important thing, how many partition you should have. How many partition, the number of partition actually is decided based on the based on the cluster configuration, and you can say that anything or requirement of the application. So just if you increase the partition, that means, or increase too many partition, if you increase too many partition, so each part have less or no data. So let's take an example. Let's say, very interesting example over here just to understand this partitioning is, so let's say we have an RDD which is having a 5 partitions, and we have done this partitioning based on the SC dot parallelize function or something else. Now in this we have a 4 cores in your cluster. I'm just giving a hypothetical example. Now each partition needs 5 minutes to execute or to process. So now based on that, based on all these, you can say that, so 4 partition, because we have a 4 core, then 4 partition runs in parallel, right? And the 5th partition will execute after 5 minutes, because this is the limit. So that means total we have they have taken 10 minutes, and after 5 minutes it is executed. That means after 5 minutes, total 10 minutes, and after 5 minutes 3 cores will be free. Only 1 core is executing the remaining core. Okay, so this give you a little idea about how the things goes. Now the best way is the number of partitions should be equal to the number of cores. Okay, and how to get the number of partition? RDD dot partition size, num partition also. If we have less partition, let's say, then what will happen? Some of the worker will sit idle. Okay, and then when the number of partitions are less, then we have a less concurrency, less parallelism, and during this state, improper utilization of resources. Right, now out of this thing, if you have a very less partition, that means out of 1000 node we have only 2 partition, that means 2 partition will be there stored in 2 nodes. And then in that scenario, what will happen? The data, all the data will be stored in these 2 files. Then there will be a data skewness. Data skewing will be there. That means to some partitions where the data is stored. Okay. Now this is the best way how we can deal with that. So now we know that what is a partition and how many partition we can do. So we have discussed what is the partitions and what is the best to choose the partitions, and how many partitions we have to do. So let's talk about the types of partitions. or types of partitioning. The first and foremost is your hash partition, hash partitioner, hash partitioning. Okay, this partitioning actually spread the data evenly across the cluster or across the partition in the clusters, across the partition based on some key, okay, over the cluster. Now we have an object dot hash code. In Java, you have studied the hash code is used to determine the partition. The hash code is used for determining the partition, something like key, hash code, and then modulus, and then the number of partition. Okay, this is the main code. And you have seen this in the algorithms and many areas. So next is your range partitions. Now this technique is very efficient as compared to other one. So this is more efficient partition technique. Now in this, we have a tuple having key with some range. Okay, and this range appears on the same machine. Now the data within the range will appear on the same machine. This is the one strict scenario. And the key in this, the keys are part based on set of sorted values, sorted keys, and some kind of ordering. Okay, so based on the keys, it will be sorted according to that. So this is another simple example of range partitions. The third one is you can have some custom partitioners based on your own logic. So this custom partition only works or only for the pair RDDs. We have a key value pair. So in this key value pair, as elements can be grouped and based on some function. Okay, based on function of each key. Now let's say, just to understand the custom partition, let's say you have a data and data is based on key, which is your country code, and then some data. So now what you can do, you can apply a logic on the custom partition that when the key code, country code is, let's say I in India, then that my data should go to the partition number 1, and then the country code is US, then it should go to 2, and similarly vice versa. So what will happen, all the data related to the same key will be available in the same machine, and then accessibility will be very fast. So this kind of partitioner is used when we don't have a default partitioner, we use the custom partition. Okay, so now that's all about the partitioner. So just to sum up this session or some of this, let's understand what are the characteristics of the partitions. Okay, so let me write the characteristics of the partition. Now you can say that every machine in Spark contains one or more partition. Okay, it will be there, and the number of partitions are configurable. So you can configure the number of partitions, you can change it. Even we have a few partitions or we have a too many partitions is not a good approach. Okay, now this partition, very important, this is very important. This partition don't span on multiple machines. That means whatever the partition we have, all the data will available within this partition, and the space is not there, it will cluster will automatically find the new nodes. That means all the data within the partition should be on the same machine. So guys, this is all about the custom partitions, characteristics of partitions. Thank you very much for attending this session. Thank you.